on your laptop, and how can you benefit from the parallelism of the hardware on your laptop. And we managed to bring, at least in the video, an application which was like about a minute, 55 seconds to less than a second by just moving from sequential application or sequential execution toward executing the same application on a GPU. And we did the same thing with sorting the terabytes on using the MapReduce framework proposed by Google. And we also see how we can bring a computation from 3 hours or 3.6 hours to less than a minute. And this just shows you the how much we can achieve by just doing the right parallelism. That was the good side of the story. But I can tell you that's not easy to achieve these numbers in a real situation, and because there are some issues that need to be considered when you are writing a parallel program. And today, I hope I will have enough time to bring those topics to you and just to explain how these things will impact your how much you will gain from the parallelism of your application. So why it doesn't. Yeah. So what I want to start, this is how I left it the last time. So high performance computing is the fact that we're going to use supercomputer, which have a lot of hardware in parallel. That's something we have discussed. And today we're going to go to the next part of the sentence, which are what are the techniques that are used to solve or to write parallel programs. And I think also I had at the beginning, I told you that parallel programming is not only about technical skills and solving technical problems. There are a lot of administrative problems, especially if you go beyond a single cluster. So if you are working within a cluster, so normally it's technical issue that you're solving. But if you go to a computing cross different cluster using grid computing or using cloud computing or using data centers and trying to solve your problem, there are more issues that are more related to administrative things. That means how the system is being run, how it is operational. So what are the limits? What are the configurations? Do they allow you to connect to any node? Or do they connect you only to connect to a specific node in the cluster? And I wanted to stress the fact that on these clusters, I mean, these systems, it's very hard to change anything. I mean, these systems are more, or especially the administrator, are more concerned with security and fair use of their resource than trying to optimize a single application. So you really have to obey the rules and go through with the configuration that exists. Okay, so and I will use the term high performance computing, supercomputing, sometimes interchangeably, or also in the literature, sometimes these two words mean the same thing. But in the following, we're going to talk about this speed up. I've showed you some speed up that I've just summarized a couple of minutes ago. But what are the factors that will impact this speed up? To do this, I'm going to do it through a very simple example. So how much you want to, for instance, if let's take the example of the program, the chemistry problem that we had at the beginning. So we had 3 different execution, a single execution on a sequential CPU. I mean, that's basically very sequential, instruction by instruction. Then we had a second one, which is on the threads on the CPU, but using the multi-threading option on the CPU, which I think it was 12 threads or 13 threads. I don't know how many threads we were running in parallel. Then we had a GPU. So if we ask you to calculate the speed up obtained, so I think an easy way, and you should all agree with me that we take the time it takes to run this program on a sequential program, then we divide it by the time it takes to run on the parallel program, then we have a speed up. So that's the easy way to do it. This is a simple way to calculate a speed up. So It's the ratio of 2 times sequential time over the parallel time. But there's a catch here. So we have first, when we calculate speed up, we have to think about the size of the problem we are calculating and we are working with. So usually we specify a certain size of the problem. If we want to sort 1 terabyte, so we should give the same terabyte to a sequential program and the same terabyte to a parallel program to be able to calculate the speed up. We should not give 2 different sizes of the problem. But this is only one side of the story. So what can we get? So we can get this type of speed ups. So that means the most logical one is the black line you see here. And that's what you expect. I mean, since we did not say anything about speed up, if you have more CPUs, if you have more threads, then the time should go linearly like this. That is something that you expect, but it's not always possible to realize. A purple line is more easy to realize and more realistic. So that basically we see that there is some speed up, but this is not really increasing by just doubling each time we have the number of we increase the number of processors. There's also this line which is called super linear, which is almost impossible to achieve, or it could be achieved only if you have really specific conditions. So sometimes you have these caching system which are at the buffer size, and if all these things are really somehow get into a good synchronization, then you can get these kind of extraordinary speed up. But most of the case you get this one. And actually what can happen is we cannot have a continuous speed up, but at a certain time, the more we increase the CPU, then we see more speed up like this, which will go down. That which doesn't make any more sense to add the number of CPUs, because we will lose in terms of performance. But the question is why we have this kind of behavior. To explain it, I think I'm going to take an example. Let's take this few lines of a program. The question is, can we run this program in parallel? We have 5 instructions, 1, 2, 3, 4, 5. I will give you a couple of seconds to see if we can run this program in parallel or not, and which part could be and which could not be. I assume that you're all familiar with programming here. We're not talking about algebraic type of operation, but there are more. This is the equal sign here means we assign the value to A. And I see something in the chat here that I think D can cause dependency on it. And that's exactly the point I wanted to make. So he saw it, I mean, Sofiane saw this. So I cannot execute 1, 2, and 3 in parallel because the value of A is needed to calculate D. So 1 and 2 are dependent. They cannot be run in parallel. Even if I have 100 CPU, 1 and 2 have to be executed in sequentially. And you're completely right. You have also the D over in here sentence. Also the D is needed before I can use 3. So this is a sequential part of the program that cannot be parallelized. So whatever hardware you have, this will gonna be executed in sequence. This is how the logic of the program has been written. However, if you look at the second part, the loop, the for loop, apparently it does not carry any dependencies. So there is no reason why I should execute 4 and 5, which is basically a repetition which is assigning this M vector value 0 for each of the value of this vector. And that here, this is quite parallel, and that it can really yes, I agree. So I saw also I had some chats here. So that yes, the value of depending on E, but if you take it once you have the E, the 4, 5 could be executed in parallel. So we can execute the 3 in sequentially. Then once we know E, we have the second part is completely parallel. So you're right. These two parts are dependent on each other. So there is dependency between 1, 2, 3 and the loop. But once we have executed 3, then 4, 5 could be executed in parallel, and makes a lot of sense. And this is very nice because usually loops. They might be million. E could be a value of 3, 4, 5 millions, and I don't want to do this sequentially. Initialize every part of my vector one by one to reach the million. That will take. I can do it in one go by just giving this kind of operation to a multi-core or GPU, and he will do it in 1 or 2 iterations. And this is basically a typical uh, use case in a program. So what we can get is always in a program is have a parallel part and a sequential part, and we cannot avoid it most of the time. There's always a sequential part, and which prevent from having these linear increase of the speed up. And this is why we said this one explanation why we have not always a linear speed up when we run parallel application. To understand a little bit the speed up, so yeah, we have to look at there are different programs. There are programs in which are really suited for parallel programming. They like, and some of them like well known. So in weather forecasting, DNA sequencing, some of them are really sequential and cannot really help you a lot when you are programming, unless you come up with a very parallel way of doing the partition of your program. And I think these days we don't see that much parallel programming. I think in the 90s there's a lot of effort in trying to come up with parallel versions, but this some smart way of programming seems to have been abandoned. It's not anymore as prominent as it was in the 90s, but still there's ways to execute this. So there's a way to uh, calculate the speed up by taking into consideration the parallel portion and the sequential portion of your program. And this shows you it's given by the what we call the Amdahl law. So it basically tries to calculate the speed up by looking at how much parallel part in your program is equivalent. So if you have 0 parallel programming, though no speed up can be reached. If you have 90% of your program is parallelizable, then you have a very big speed up because this fraction will be very small. But he, of course, he considered that this is done at a fixed size problem, that we don't have different size of problem. But since we have a fixed size of our problem, what's going to happen is that the fractions of code of execution we're going to give to each processor is going to be smaller and smaller. So we have 1 terabyte. We want to sort a terabyte. If you have 2 processors, we give them half terabyte, half terabyte. If you have 4, we have quarter of terabyte for each 4 processor. If you have 100 processors, then it's going to be. So the amount of computing that's going to be given by for each processor is going to be smaller and smaller, and this will also prevent the speed up. So this is another way of looking at the Amdahl law, which consider the number of CPU that's going to be used to execute your parallel program, and depending on the portion of your parallel code. And you can see there's kind of bound in the limit that we cannot reach beyond it. So you see, for instance, here that it doesn't make any more sense in this case to increase the number of CPUs in this region, because the speed up will not increase anymore. It's more, I should say, beneficial if you use 500 CPU to give you almost the same speed up as if you use this amount of CPUs over here. This seems to be saying that we don't need large systems because of this limitation, but actually this is only limited by the size of the problem. And because those systems are meant to, the big systems are meant to solve bigger problem. So there's another law, which is called Gus-Jefferson laws, which say, okay, if we don't fix the size of the problem, then it makes sense to create a bigger and bigger machine, because we can solve bigger and bigger problem, and that's the speed up can increase. So if the Amdahl law is looking at the instructions, the part, because he's just look at the instructions, and if we have part of the instruction is somehow linked to each other, depending on each other, then you cannot increase. And the other one is the Gustafsson law, is just looking at a data parallelism, and that we say the more data we have, the more we can use bigger machine, the more we can get some CPU, some speed ups increase. So that's a very small introduction to how we can what can have impact on your speed up. Now, how can we design a parallel program? We have already seen something last week. So we said 2 dimensions, the data or the instructions. And that's the only way we can parallelize our program. The easiest way is to parallelize on the data side. That means we take the data, we cut it into pieces, and then we start processing those pieces as independently as possible, and then progress. At a certain time, we need to synchronize, and then we have to make sure that all the tasks get the data, and we can continue to the next steps. The other way, we can do a kind of pipeline, or do the decomposition of our library functional decomposition, and then we assign each task which does something different, and we organize them in a pipeline or in a graph, and then we start processing our program in parallel. So that's these are the 2 ways we have seen. So the first one, I'm repeating here a little bit myself. Data is cut into pieces. I send the data to the different processors. I assume that within in this part of the data, there is not, we don't need the information on the other data. Otherwise, it doesn't make sense to make this kind of cut. Usually what happens is that you need to transfer data between these two parts, and then here. So there's a bit of communication at a level where you cut the data into pieces, something. And that's the art. I don't really see it. That's what will impact your performance. So if you're clever enough and you know how to divide your data, you have to minimize this kind of communication over here, and that will give you the best performance. This kind of approach is quite very popular. Most of the big data platform are based on this type, very simple way of parallelism. So that's, for instance, the MapReduce I showed you last week. It's basically doing this, but at a very large scale. So yeah, and it automates a lot of operations. Okay. So the difficulty here is to find how to divide your data. That the main objective when dividing it is to minimize the communication, because communications are inevitable. So they have been introduced by the fact that we have cut our program into pieces and we're running them in parallel. And every piece of our program is having a part of the solution, and then we need to combine it. And when I combining means that we need to communicate between the processes. How do you cut this? These are more 1 dimension, 2 dimension, even more complex way of dividing the data. So this is one of the project we are doing here at the eScience Center. So they want to simulate I think here the idea is to simulate the flow of water in the ocean. I have a small video I can show you at the end if we have time. So how this project is being set up to simulate the data. And then you can see here, because we are interested in only in the ocean, we are not interested in the land. So the data has to be somehow divided between our CPU in a fashion that we should minimize the combination. And we know that, for instance, that it's clear that this part of the ocean does not have that many impact on this one. So we can do some work here without having to communicate with data which is communicated over here. So that's this kind of specific decomposition of our data. And the idea behind this is to do 2 things. I've already talked about. One is to minimize the communication. The other one is to minimize the load balancing. I will talk about load balancing in a couple of minutes. So that is the difficulty in this data parallelism, is how can you cut the data into pieces to minimize communication, at least for now. The other parallelism is what we call functional parallelism, and then basically it looks at the instructions or at the program, and how can we cut this program into pieces in order to establish a kind of pipeline or a graph of data that could be executed in parallel. So depending if we have a pipe, if we have a continuous flow of data, so a pipeline is the best way to do it, and then we start processing the data in a continuous flow. If you have data which is basically could be processed for with multiple models, then we have a kind of parallelism. Then we have a spout where the data is split in between the different models. Then we do them in parallel. Then after that, we get the data back and continue with different models like ensemble of programming. These kind of techniques always are based on functional programming. Here's the same example I've shown you before. So this is the code that they were trying to use to do the simulation in that project. And you see the blue part is the program code, the code which was dedicated to simulate the ocean. We have also pieces of the code which is dedicated to do simulate the ice, the land. And you see the red part are the couplers, which basically need some to communicate data between the different processes. And this is now the number of cores that has been split between the different part of your code. So in this case, we know that the ocean takes a long time of calculation without any communication. This is why we give a certain number of cores, why the other part of the code have been given a small number of cores over here, and they are being coupled from now on a regular basis over here. And at the end, when the ocean simulation is reached, then we do a big coupling at the end of the program. So that's an example where you can see the data decomposition and also the kind of functional decomposition. We have seen the data dependency before. So we said that if there's a data dependency in your program, that is not good for parallelism. There are three ways of creating dependencies when you have multiple tasks. Either you are trying to read and write from, that's what we call true dependency. So one task will write a value in X and the other one will try to read it. And if these two are not well synchronized, then task two will either read the wrong version. So if it's too early, then it reads a version of X, which is not the one that is meant to be read. And you have also the dependency if they all both try to write to the same place. And so we have a task which want to write the value to the memory place X, and the other one also write the same value to the same X. And kind of there's a kind of concurrency, who should access this value. And depending who's first, we can read different values, and this kind of indeterminism over here. And you have the other way around, which is the read by a certain task and the write by the other one. So these are the dependency that could occur in your parallel program between different tasks in this case. The other problem that might impact your speed up is the load balancing between the different processors. And you see in these examples here, we have a 4 tasks running, and then you see that task number 2 is taking much more time than task number 1 or number 1 and number 0 and number 3 and number 4. These are the tasks. So we are always limited by the slowest machine or slowest task in our programming. This is not really good because we have a lot of CPU available here and here and here. We are not misusing, because just the way we wrote our program, we got this type of speed up, which is limited by these tasks. But if we could rebalance this amount of computation to the other tasks, then probably we could be able to finish earlier. So if I take this part and give it to task 0 and maybe a little bit to task 1 and maybe to task 4, then I should be able to finish somewhere over here, and I will have gained all this time. So load balancing is very important in parallel programming. Make sure that the tasks you have exactly the same amount of work to do. And this is not always obvious. I mean, sometimes it's easy to see to reach. Sometimes you need to do a bit sophisticated approach to get to this situation. And actually, sometimes it just over the time when the program starts, maybe at the beginning start balanced, but if it contains some dynamic parts, some part gets into imbalance easily. Then the best is that you have a system that could kind of reactivate the balance between the application. And actually, that's the example of the I gave you before is a clear example. If I just take the data, I cut it and give it to 4 CPUs here, then fortunately this CPU will have you have all this piece of data which is not really interested in because we are in the ocean. This one will have a lot of things to calculate because there's only this part, and this one might have a lot of also a lot of white place that we don't want to calculate, etc. So this is not really the way we should balance the data between our processors. So because communications are needed, so the easy application to parallelize are the one called embarrassingly parallel application. Usually we do data parallelism on them, and there's plenty of examples of these type of applications out there. Monte Carlo simulations, city at home, Jacobi, these kind of things are not really suited for your application. Communication are needed for a parallel program, but they come at a certain cost. So when we look at the communications, how we have the cost, because it has to, applications need to send it to each other some data. And when we send data to each other, we have to use network. Then there's latency involved in this, because especially if you are programming beyond the a single cluster, so latency become very, and the bandwidth available to you becomes very important. Suppose you're going to send your terabytes from between 2 data centers, even if they are located in the same region, you are limited with the bandwidth of the data existing on between the 2 centers. And if you start doing on the global scale, so if you're having an application which is running all around the world, you have also the latency of the communication that comes into play. There's also the way, how do you organize your communication? Are you going to make them synchronous? Then there's this kind of blocking state where the application has to wait for the other before it can continue and until it gets the data, or you're going to do it in an asynchronous way where somehow there's, when the data is available, just put it in a kind of buffer, and later on the other application can come and get it. What type of application do you have? Do you have a point-to-point communication, or you have an application which sends data to all over the other tasks? That all these things could help you to minimize the impact of the communication on your computation. We have a question from Sufyan again. A load balancing in function of time and function of a number of tasks. In function of a number of tasks. I think if I understand this question correctly, so a load balancing is in here. We are, what I'm mentioning is in terms of the amount of computation given to every CPU or every computation unit in your ensemble. So if you have 20 elements, you want to make sure that they get the same amount of work to do. Of course, it depends on if we suppose an homogeneous architecture that all the CPUs are the same, they have the same architecture, the same memory, the same things, and then we assume that we give them the same amount of data and they should be able to finish in the same amount of time. If we have a heterogeneous architecture, this is a different story. But at the end, load balancing makes sure that your program or your different part of the program should finish within this more or less the same amount of time. We don't have one application that takes 2 hours to finish and the others finish in 25 minutes. So that's what I'm talking, and I think your question is in this, and I hope I have answered your question. Okay, so one way to get a way with the communication, and is to make them overlap with the computation, which means if make sure that your CPU is doing something while it's waiting for the for the other CPU or for the other part of the program to finish its execution. And for this one, to achieve this, then we have to go with non-blocking type of operation. That means we don't have to wait for each other to communicate the data, but we have to have in our environment a kind of system which is able to keep the data for the second part to come and get it at a later time. In the meantime, the program that is waiting, instead of just waiting for the program, the data is not there, so he just go do other tasks if possible, then come back and get the data when it is ready. Then we don't need really a synchronization. So in this way, we can kind of hide the communication with the computation. So that's the best way to achieve high speed up and very good parallelism. There are, in terms of the techniques you can use for load balancing. So I have already mentioned some of them. At least the one which cut the data into pieces. If the data is a matrix or an array, you just make sure that the data is distributed uniformly on the processing unit you have. If you have a loop, you're going to divide the iterations between the different the different processing unit, etc. But this is making a strong assumption that every iteration is the same, which is not always the case. So some iterations might take more time than others, and this is why I'm saying this kind of static division of the data of the operation is not going to be effective if you have a dynamic load. If you have a sparse data array, for instance, with a lot of zeros in it, then giving a piece of chunk of data to a processor which contain only zeros, and then the computation will be finished in no time. While on the others, if another part is going to be given a more strict data, then it will take more time, and that's not going to work. A more easy and more reliable way of achieving load balancing is to use what we call scheduler with a task of pools, pool of tasks, sorry. And that's very simple to explain. So suppose you have here, your parallelism could be this divine in number of, instead of dividing the data and assigning the data to the processing unit, you just divide your data, or your, usually it's based on the data, into parts, and every part will be a task that could be assigned to a processor, and then the processor will come and fetch the data to process. They do, when they finish, they come and fetch the second data. In this way, the faster will process much more than the others. If we have a slow machine here, which is not able to process as fast as the previous machine, it will do less work, but this one will do the other most of the time. It's not going to be waiting for this task to finish, but it can just grab another task to do, and grab another task to do, etc., until it finish all the tasks. And if this one is very slow, it will have done only one. And in this case, the problem is not in the way the parallelism have been approached, but it's in the choice of your computing resource, which is very slow. You should, maybe if you are in a cloud environment, you just get rid of this machine, reserve another machine which is faster, then we have a higher parallelism. So there's another question. So when we talk about load balancing, for example, in terms of time, communication, and thermal and energy, is it right? Yes and no. So usually it depends what you want to put in the front. Usually there's a trade-off. So if you try to optimize for the time, the load balancing will have to consider only time and computation. So for us, energy is not very important. So because I want to finish as early as possible, even if it costs me the energy of the world. So now if you want to be green, and that's the way we enter into the realm of green computing, we want to create a trade-off between the energy you're going to dissipate by the computation and the time we want to achieve. So there's no black and white here. So if you want to be green, then you have to optimize the use of your CPU, your energy, and then you have to think about it as a way to organize your parallelism. But there is no. I think if you consider this kind of energy things, then you have to really come to a trade-off between what you could achieve in terms of performance and what you are going to pay for energy. So if the more you want to be green, of course, I guess you will have to do less. Maybe parallelism and just use less CPU, or maybe try to efficiently use the CPU. There are different techniques for green computing. But at least for this, what I'm talking about here is just trying to speed up the application as fast as possible. So we don't really care about the thermal, but I agree that if we have to go into the green computing part, we should take into consideration that part also. Okay, so the third point that might impact your parallelism or the approach to your parallel program is the granularity of your code. And we have already seen it when we had this I have introduced the Amdahl law, because if we consider that we are in a fixed size of the problem, increasing the number of processing unit will just make the granularity of the computing smaller and smaller and smaller, and the benefit of having parallel system will disappear at a certain time. So the granularity is always calculated in terms of what should you spend on the computation relative to what your communication. A program which communicate all the time is not really a good program. So you have to minimize the number of communication and give a way to do more computation locally, instead of just keeping communicating between the processing. Communication comes always at a cost, even within even within the node. For instance, I will put a link later on about the project, eSalsa project, about the simulation of the ocean, and when they were trying to port the code to the GPU. So even on the board, they consider that moving the data between the CPU and the GPU is the bottleneck. So even for us, it's something which should be very fast. This is still a very big problem. So if we do a bit of computation on the GPU, then keep moving the data from the CPU to the GPU, from the GPU to the CPU, it's not going to impact our performance. So make sure whenever you're writing a parallel program that granularity is very important, especially if you go to this big system where takes you maybe few minutes or a few hours to get to the resource. And after that, when your job gets into the machine, it executes for a few seconds. This is really a waste of time. And then you will not get any benefit from the parallel machine. Because next time you would like to get to the GPU again, you have to go through all this overhead, which is part of the infrastructure, and then you execute again a couple of seconds. That's not going to work. So when you consider a parallel program, you always need to think about this granularity. And here I'm just giving you a few examples here. There's a good program because here we do a bunch of computation before we communicate, big bunch of communication, while this one is going to be less performant because we do bit of communication, etc. And this comes at a very high cost, especially if you are considering blocking type of operations, where most of the time the processing unit will be waiting for each other to get the data and give the data instead of doing some real computation. Okay, so when we do parallel programming, there's also pitfalls that can happen quite often, which is a notion of deadlock, life lock. The deadlock, because now we have a different part of our program, which are somehow they are communicating. eh, they are communicating, which means they are sending and receiving data. Yeah. Okay. And depending if the two programs are scheduled at the same time or this one gets some issue before it gets run, then we can get easily into a deadlock situation where the program does not progress anymore because this communication will not happen for some reason. So if this one blocks at the send operations and this one blocks at the receive operation, that it might be that a certain time this send and receive operation is not completed and the two processor will not progress, and what we have at this time we call it a deadlock. And this is really really difficult to debug when you have a parallel program, especially when you have this paradigm where you have an explicit uh, uh, way of defining the communication, like in MPI, when message passing, you have usually it is up to the programmer to define this communication, um, this communication operation, and to add them to your code. And this is oh yeah, and programmers they don't see the whole pictures, and then that they don't see all the ways that these tasks are being scheduled on the supercomputer, and they can get them easily into a deadlock situation. A live lock situation is that also that can happen if you just make a small mistake in your program and you create an infinite loop, and then basically your program, one of the part of the program gets into a definite loop, never gets it, so get out of this infinite loop, then never manage to communicate the data at the right time to the other part of your program, and then what you get in fact is just another kind of deadlock. We just call it life log because it's due to an infinite loop. So these are the parameters that might impact your the speed up or maybe the benefit of a parallel architecture. I will summarize them here. So that is, we mentioned granularity, load balancing, and the communication. And we just went briefly through a couple of techniques which can help you to try to get these elements at the right level, which make sure that your application progress and get benefit of the parallel architecture it is given. How I can do it? Okay, so we're the rest of this lecture is going to be going through a couple of uh, ways we can parallel our applications. So there are tasks and data parallelism based on either the architecture, if it is shared memory or distributed memory, with message passing or with threads. But also you have also the certain paradigms which reflect the Flane taxonomy, where we want to execute a single program on a multiple data or a single or multiple program on multiple data. The only difference is that here with reasoning at the level of a program and not level of instruction. As this is what that's because remember that we were talking about instructions here. Here we're talking about programs, not instruction. How we do that? So there's no magic stick here. So if you want to write a parallel program, you need to modify a little bit your sequential program, the one you have started with and you have implemented on your desktop machine. There are different way of doing it. So there are low level ways of parallel programming, quite difficult, quite tricky uh, to program. I mean, I would say to use, and not suited for any domain scientists. And this is why big data platform are trying to get away from this type of approach to parallelism. Uh, and we will start with the most common one. It's called the MPI, message passing interface. It's really used, heavily used in HPC domain. So you have two processes on your machine. And those processes, in principle, if you have, they should not communicate. Processes in our machines, they run next to each other on the hardware, and we have a nice operating system which makes sure that these processes never get to conflict, and they run, and we're happy with all our operations running on our machines. But if we want them to behave as a program, then we have to make sure that the process can communicate. And that's basically what machine message passing interface is about. It's an interface or that could be added to your program and can make sure that the data could be sent from one component to the other. So it's an inter-process communication with different address spaces, different things, which are not meant to be communicating, at least from operating system point of view. So here we called, this is an explicit send and receive operation that have to be programmed by the user. So yeah, data, process one, send the data to process two. There's an operation that send, the other one has to get the data and progressively read the data and store it somewhere and progress in the execution. Okay, so what can you see here?
Adam, is 350? Yes. It's up to you what you want to do.
It's 3:50, so time is going fast. I was planning at least to. Let's see if we have questions or beside the one we have already asked. Maybe if you have questions, then go for the questions. Otherwise, I can just use the 10 minutes to progress further. Questions? We had a couple of questions during the, so I hope I answered them all. So we had a question from Sofiane about load balancing. Then we have a question about, yeah, are we optimizing the time or are we optimizing energy? That also was a question that I tried to answer. I think Dels, earlier you said that developers stopped coding parallelism. Yes, Doug, I think maybe I was not clear on that point. Yes, at least to my knowledge, I think I've seen in the 90s really people thinking about parallel program. Parallel program really, it's not a matter of cutting the data into pieces or saying that this function goes to, the entire approach of the program is completely different from a sequential one. And it's, I have to admit, it's not an obvious way to do this. I mean, you look at the program and you see why you don't understand why he's doing this and that because it does not follow the sequential logic. We, as a human, are used to think in a logical way, in a sequential way. So if you look at the program, you say why he's doing this, why he's doing that. But actually, it's like playing chess. I mean, you don't understand all the intermediate step until you get to the checkmate at the end. And that was a really nice way to do this. It's very complicated. Not everybody is able to program in that way. So I think today, in my opinion, again, it could be different. Yeah, someone else will tell you a different story. I say we are going for the easy solution. Yeah, we have computers, we have CPUs, they are cheap, they are there. Just go for the less intelligent approach. I will say this is what I wanted to say. So it's, I'm sure there are still there's still research in this parallel programming way, but is as not as prominent today as we see it today, because today is basically 90% of the is based on data parallelism, simple parallelism, embarrassingly application, and we don't need to go for the complexity anymore because yeah, there's plenty of CPU around. And for a small amount of money, you can get a large number of CPU on a cloud system. So you don't really need to be smart. So that's what I wanted to say. So I'm not discouraging people from really looking for a very nice parallel program, but that's the fact. What I. Any other questions? So if you allow me, Mohammed, just I want to finish the MPI part. So Yeah.
Yeah, go ahead.
So that's so just a few words about MPI. Yeah, of course we cannot talk about MPI in 5 minutes. I think we need a little bit more. Uh, I might introduce maybe at certain time. I don't know if you're going to do it next week or the week after or somewhere in the future. Maybe I dedicate 45 minutes to MPI to explain how it works. Maybe, and I also can point you towards some tutorials online which can help you to write your first program in MPI. So as I said, MPI has been widely used in parallel programming, HPC. It's not an easy way to program, especially if you're not a computer scientist. You can get easily into a deadlock situation because you're programming explicitly the send and receive operation between the different part of your program. But MPI has been optimized for good performance on the clusters and these supercomputers. They use shared memory. They use the memory enter the different nodes of your system using this network, fast network. Uh, so they are very good environment on HPC clusters to achieve high performance. As I said, they can get into the deadlock. I think I've already said this one. They are very good for distributed large computation across reliable networks. So this is something very important. If you take the standard MPI type of libraries, they work only on reliable networks. So if you want to use MPI over a wide area network or cross cluster, it's going to be failing because the network is not reliable and will give you you get into trouble. Actually, there's some version of MPI like GMPitch, which has been somehow modified to allow communication over a wide area network. So I think I've talked about deadlock. I've talked about the MPI. I think, yeah, this is a simple MPI hello world. So very simple program in C. It has one line, which is just print the word hello. So if I want to, as I said, there's no magic. If I want to have a parallel program or parallel version of this program, I need to add some code. Here, there's the code needed to write an MPI program. These are the, but if we have a lecture on MPI, I will explain what these what these lines mean. They are needed. Some of them are mandatory. You need to initialize, you need to set up certain things, and then you define how the elements are programming. This is a very simple example. We don't have really communication because the processes, they don't communicate. They just print uh, the hello message word on the screen. And then if we compile this program and then run it by giving the number of processor we have, giving certain file configuration file about the system, then we will see that we have a number of processes that have been started and they all say hello. And the idea here just they say hello from, they give you the rank. So every program in MPI has a rank. This is a processor the rank 1, 0, 3, 2, and just say I'm 1 out of 4. I'm 1 because I'm running here 4 jobs as a simple example. And I think I will maybe finish it here. Like next time I can talk about OpenMP and shared memory type of parallel programming. And that will complete finally hopefully the introduction to parallel the parallel program introduction. Do we have still a couple of minutes before we finish the hour? Yeah, we still have 5 minutes. We have room for more questions.